In this video, we will continue our lesson on 3.4 and learn molarity of ions and dilutions. When an ionic compound dissolves in water, it dissociates, which means it separates into individual ions in the water. The ionic compound no longer exists as a compound with the ions stuck together, but instead they are floating around in the water separate from each other. This happens because the ions are more attracted to each other than they are to each other. As we will learn in a later chapter, water is a polar molecule, which means it has a partial negative charge at one end and a partial positive charge at the other end. This is why the negative and positive ions are attracted to water molecules and separate away from each other in water. This is a great picture of dissociation. When NaCl dissociates in water, you now have a sodium ion and a chloride ion in the water. You must write the charges on the ions because neutral sodium and neutral chlorine are very different with very different chemical properties. If you have two compounds of sodium chloride, then you'd have two sodium ions dissociated in water and two chloride ions dissociated in water. And you'd have a total of 4 ions dissolved or dissociated in the water. If you had 1 mole of sodium chloride before it dissociated, then you'd have a total of 2 moles after it dissociated. 1 mole of sodium ion and 1 mole of chloride ion. Solid neutral sodium is a soft grayish metal that is soft enough you could cut it with a butter knife. It reacts explosively with water or even with the sweat on your hand. So, it is always stored in a jar of oil to keep it away from any water molecules it may come in contact with. Solid neutral sodium is also quite toxic, even in small amounts, so we don't have any in our chemical storage here on campus. The next picture is chlorine gas. When chlorine is neutral, it is a diatomic element, which means it exists as 2 chlorine atoms covalently bonded together. It is gaseous at room temperature and has a yellow color. Cl2, or chlorine gas, is a poison used in chemical warfare to kill people. So, both sodium and chlorine are dangerous to be around when they are neutral. But if the sodium transfers an electron to the chlorine and they make an ionic compound, sodium chloride, that is table salt, and it is actually something our bodies need in small amounts. When it dissociates in water, we have sodium ions and chloride ions that are not dangerous to humans. Here's the first practice problem. If you have 2 moles of the ionic compound barium chloride and you drop it in water, how many ions will you have after it completely dissociates? So first, we have 1 barium and 2 chlorines in our chemical compound barium chloride. When it dissociates in water, the barium ion, with its 2+ charge, is going to separate from the 2 chloride ions, each with their 1- charge. In this problem, we have 2 moles of the barium chloride. So when it dissociates, you'll have 2 moles of the barium ion and 4 moles of the chloride ion. Here's our next practice problem. If you have 3.5 moles of the ionic compound magnesium phosphate and you drop it in water, how many ions will you have after it completely dissociates? 1 magnesium phosphate is like this, where you have 3 magnesiums and 2 phosphates. Phosphate has 1 phosphorus and 4 oxygens covalently bonded together, and it all together has a 3- charge. Those oxygens do not separate from the phosphorus. Oxygens do not dissociate into ions away from the phosphorus. The entire phosphate, the PO4, separates from the magnesiums. Because of this subscript 3, we're going to have 3 magnesium ions, each with their 2+ charge. And then with this subscript 2, or because of that subscript 2, you have 2 phosphate ions, each with their 3- charge. So if we have 3.5 moles of the magnesium phosphate that's going to dissociate in water, then we're going to end up having 3.5 times 3, which is 10.5 moles of the magnesium ion, and then 3.5 times 2, which is 7 moles of the phosphate. So when it asks how many ions will you have after it completely dissociates, we have a total of 17.5, 10.5 plus 7, ions dissociated in water. 10.5 moles are magnesium ions, and the other 7 moles are phosphate ions. Dilution is the process where the concentration of a solute in a solution is decreased by adding more solvent. So you can dilute your iced tea by adding ice cubes. You can dilute your coffee by adding more water. Chemical solutions come in highly concentrated solutions called stock solutions, and they're around 10 or 12 molarity. In a lab, a chemist may need 0.5 molarity of a chemical, or they might need 0.25 molarity, or maybe 1.35 molarity, etc. You can see how there are many different concentration values that a chemist may need for their lab experiment. So instead of purchasing all of the different concentrations for every different chemical, they just buy the highly concentrated stock solution and then dilute as needed. However, a chemist needs to know exactly how much water to add to exactly how much of the stock solution to make just the right concentration needed. Our molarity equation is this, if you remember. Molarity, capital M, is equal to moles over liters. When you multiply liters on both sides of the equation, we get moles is equal to molarity times liters. The sub 1s refer to before the dilution, and then the sub 2 on each of the variables refer to after the dilution. When we dilute a solution, we don't add or subtract any of the moles of solute. Instead, we just add solvent. So, moles of solute before the dilution is equal to the moles of solute after the dilution. We can substitute into the equation our M1L1 is equal to M2L2. However, this equation is usually written as M1V1, which is equal to M2V2, where V means volume. In this equation, the V can be any unit, milliliters or liters, or even gallons or quarts, as long as you're using the same volume unit on both sides of the equation. Let's go ahead and look at our periodic table. Our dilution equation is on the back in our miscellaneous equations box, and it's the very last one. Here's our first practice problem. If 0.85 liters of a 5 molarity solution of copper nitrate is diluted to a volume of 1.8 liters by the addition of water, what is the molarity of the diluted solution? So we have our equation that includes M1 and V1, M2, and V2. You can see we are given 3 values, or 3 numbers, 3 of these variables, and we can solve for the 4th one using some simple basic algebra. Looking at the first sentence here, if a 0.85 liters of a 5 molarity solution is diluted, that tells us that the first 2 numbers are the 1s, or the before dilution. So 5 molarity is equal to M1, and 0.85 liters is equal to V1. We are diluting this solution to a volume of 1.8 liters, and that is our V2. And we are solving for M2. Here's our original equation. If we divide V2 on both sides of the equation, then we can isolate M2 on one side of the equation, and that way we can solve for M2. So our equation then looks like this. M1 V1 divided by V2 is equal to M2. Now we plug in all of the numbers that we have. 5 molarity for M1, 0.85 liters for V1, 1.8 liters for V2, and then we can plug it into our calculator and solve. We get 2.36 molarity. Notice that our liters canceled and we're left with molarity in the units, which is perfect for solving for a concentration. There is the problem all worked out. Here's our next practice problem. Pause and try to work out this problem on your own before moving ahead to see the answer. Here is the answer, 0.102 molarity. The new or second molarity should always be less than the original molarity because we are diluting, making the concentration less. And the new or second volume should always be more than the original volume because we are adding solvent to the solution, so we should always have more volume after the dilution. Here's another problem. Pause to work it out on your own. The answer is 41.25 milliliters. We don't need to convert to liters here. The molarities cancel, and we are left with milliliters in the answer. The problem asked for milliliters, so we need to leave the answer this way. Here's the last practice problem. Pause to work it out. The answer is 0.314 liters. The molarities cancel again, leaving the answer in liters. Because the problem didn't specify which unit, we can leave the answer in liters. However, if you did take the extra time to convert it to milliliters and get 314 milliliters as your answer, this wouldn't be wrong as long as you used the correct unit. It's just not necessary to take that extra step to convert to milliliters if the problem didn't actually ask you to do so. Now you can complete all the problems in practice set 3.4.